Welcome back to Human Mimics. In layer 1, we controlled how much the model outputs. In layer 2, we controlled how much context we send in. Both of those layers assume one thing, that we are going to call the model every single time. Layer 3 asks a different question. What if for some requests we don't need to call the model at all? That's call reduction. And the first technique in this layer is the simplest one in the entire series, exact response caching. One of the easiest ways to reduce AI costs is exact response caching. The idea is simple. If the exact same question appears more than once, don't pay the model to generate the same answer again. The first time a question is asked, we send it to the LLM, generate the response, and store it in a cache. When the identical question comes back later, we skip the model entirely and return the saved answer instantly. Without caching, every repeated question triggers another API call and another cost. With exact response caching, only the first request costs money. Every identical request after that becomes a cache hit. This is especially powerful for customer support bots, FAQ assistants, coding helpers, and knowledge bases, where the same questions are asked again and again. The result? Lower costs, faster responses, better scalability. Same question, same answer. Pay only once. Let's see how exact response caching works step by step. Every request first enters the system and goes through a cache check. The system looks for an identical request that has already been answered before. If an exact match is found, that's called a cache hit. In this case, the stored response is returned immediately without calling the LLM. That means zero API cost, lower latency, and a much faster user experience. If no match is found, that's called a cache miss. The request is then sent to the model and normal input and output token costs are incurred. Once the model generates the answer, that response is stored in the cache and returned to the user. The next time the exact same request arrives, the system can skip the model completely and serve the cached answer instead. In other words, the first request pays the full cost, while all future identical requests are answered instantly from the cache. The key idea is simple. Same request, same response, pay only once.
Now, I want to stop on that word exact, because it's the whole limitation of this technique. This is a hash match. The new request has to be byte for byte identical to something we've already seen. What are your business hours and what are your hours are two completely different cache keys. One typo, one extra space, one rephrasing, and it's a cache miss. The model gets called like normal. So this technique works great for high repetition, low variation traffic, FAQ bots, static lookup tools, anything where the same literal string comes in over and over. It does nothing for open-ended chat, creative writing, or anything where users phrase things differently every time. That's a different problem, semantic caching, and that's next episode. Today, we're keeping it simple and exact.
Now let's talk about one important limitation of exact response caching. Caching works using something called a hash match. That means the new request must be byte for byte identical to a request we've already seen before. When a request arrives, the system generates a hash value from the exact text and compares it with hashes stored in the cache. If the hash matches exactly, we have a cache hit and the stored response is returned instantly. If the hash is different, even by a single character, we have a cache miss. For example, what are your business hours and what are your hours may mean the same thing to a human, but to the cache, they are completely different inputs. Different words create different bytes. Different bytes create different hashes. Different hashes create cache misses. Even tiny changes can break the match. a typo, an extra space, different capitalization, missing punctuation, or a simple rephrasing. Any of these changes will generate a different hash value. When that happens, the cache cannot reuse the previous answer. The model gets called like normal. You pay the full input cost. You pay the full output cost. The key takeaway is simple. Same byte, same hash, same response. Pay only once. Different bytes, different hash. Cache miss. Pay full price.
This slide explains that there are two types of AI caching, and although both aim to reduce cost, they work in very different ways. On the left side, we have exact response caching, which is something you build yourself inside your application. The idea is simple. The first time a user asks a question like, "What are your business hours?" your app sends the request to the LLM, gets the answer, and stores that final answer in your own cache or database. The next time another user asks the exact same question, your app finds the cached answer and returns it directly. In this case, the Claude API is not called at all. The model does not run, and the cost is zero for that repeated request. On the right side, we have Claude prompt caching, which is built into Claude's API. This does not cache the final answer. Instead, it caches the repeated input context, such as a long system prompt, a large company handbook, tool definitions, or repeated instructions. So when the next request comes in, Claude is still called, and the model still runs. But Claude can reuse the cached repeated context and charge less for that repeated part of the input. The user's new question and the model's new output are still processed and billed normally. The table at the bottom makes the difference clear. In exact response caching, there is no API call, the model does not run, and what gets cached is the final answer. In Claude prompt caching, the API call still happens, the model still runs, and what gets cached is the repeated input context. So the savings are different. Exact response caching avoids the call completely, while prompt caching reduces the cost of repeated long prompts. The key takeaway is exact response caching means don't call the model. Prompt caching means call the model but pay less. Same word, caching, but two different mechanisms and two different ways to save money. This slide explains what actually gets cached in Claude prompt caching. The most important point is this. Claude does not cache the final answer. Instead, Claude caches the repeated prefix. The repeated prefix means the beginning part of your prompt that stays exactly the same across multiple requests. In your prompt template, Claude sees everything as one long text. It does not think in terms of Python variables like context block or user question. It only sees the final prompt text that you send to the API. So, if the instructions are repeated at the beginning, they can be cached. And if the same context is also repeated after the instructions, that context can also be cached. But the user question usually changes from request to request. Because it changes, it is not part of the cached prefix. That part is billed normally. Now, let's look at the three scenarios in the middle of the slide. In case 1, the user asks a different question, and the RAG system retrieves a different context. For example, one request retrieves refund policy information, and another request retrieves business hours information. Here, only the fixed instructions are repeated, so the saving is small. The new context, the new question, and the output answer are billed normally. In case 2, the user asks a different question, but the RAG context is the same. For example, every request includes the same full FAQ document. Here, Claude can reuse the instructions and the same large context. So the saving is much bigger. Only the new question and the new output answer are billed normally. In case 3, the exact same question comes again. With Claude prompt caching, Claude is still called. The instructions and context may be cheaper because they are cached, but the model still runs and generates an answer again. So the cost is reduced, but it is not zero. If you want zero cost for the exact same question, you need exact response caching outside Claude. That means your own application checks whether this exact question was answered before. If yes, your app returns the stored answer directly. Claude API is not called at all. Cost equals zero. So the simple rule is this: repeated text from the beginning of the prompt can be cached and charged cheaper. Change text like a new question or new RAG context is billed normally. The final answer is never cached by Claude prompt caching. For repeated identical questions, use your own exact response cache. Same word, caching. Two different mechanisms, two different savings. Same usage block we've been tracking all series, but today it's telling us something new. On an exact cache hit, there is no usage block. There's no API call made, so there's nothing to meter. That absence is the savings. 100% of input and output cost for that request gone. On the prompt caching side, the usage block grows two new fields: cache creation input tokens for the first call that writes to the cache, and cache read input tokens for every call after that reads from it. Reads are billed at roughly 10% of standard input price. Let's put both of these into real numbers. This example shows when cache read tokens can be smaller than cache creation tokens. In the first call, Claude receives a full prompt that contains system instructions, context A, context B, and the user question. The system instructions tell Claude to act as a helpful customer support assistant. Context A contains the return policy. Context B contains the shipping policy. The user question is, what is the return window? In this first call, Claude has not seen this reusable prefix before. So Claude writes the repeated prefix into the cache. That cached prefix includes the system instructions, context A, and context B. In our example, the system instructions are 50 tokens. Context A is 100 tokens. Context B is also 100 tokens. So the total cache creation size is 250 tokens. That is why the usage block shows cache creation input tokens equals 250. The user question is not cached. The model answer is also not cached. They are billed normally. Now look at the second call. The second request sends the same system instructions and the same context A. But this time, it does not include context B. The new user question is, how do I return an item? Because the second request repeats only part of the original cached prefix, Claude can reuse only that repeated part. It can read the system instructions from cache. It can also read context A from cache, but it cannot read context B from cache because context B was not sent in a second request. So the cache read is partial. In our numbers, Claude reads 50 tokens from the system instructions and 100 tokens from context A. That gives us 150 cache read input tokens. This is smaller than the first call, where cache creation input tokens was 250. So this example proved the key point. Cache creation means how many tokens Claude wrote into the cache. Cache read means how many tokens Claude successfully reused from that cache later. Sometimes, cache read equals cache creation. That happens when the next request repeats the full cached prefix. But sometimes cache read is smaller than cache creation. That happens when the next request repeats only part of the cached prefix. The important rule is simple. Repeated text from the beginning can be read from cache. Missing or changed text cannot be read from cache. The new user question is billed normally. The new model answer is also billed normally. So in short, write once, read later. Read can be full or read can be partial. It depends on how much of the original cached prefix appears again in the next request. Hello, this is the lab part. In this lab, we will show what's the difference between exact cache and the prompt cache. Firstly, we start with exact cache. As you see, There are multiple steps, okay, for implement this code. I will go to final result to check, to understand, okay, what is meaning by exact cache. And this was the whole Python notebook. You can drop your comment if you want, and I will share it. Okay, let's go to the final results to discuss. Okay, let's see the output. This is user questions. So the user question is integrated with the system product, and this is unique API call for the models. Okay, this API call with count input token and output tokens, and also the cost. This another questions that is different than first one. Same way, API call and the count for input and the output tokens and the cost. Here, when I come, user come back and they are asking the same questions. What are your business hours? You see here, the API call is no. No API call implemented or done in this step, because it is repeated questions that already cached from the first one. And the input tokens, output tokens count is 0, and the cost is 0. So for exact cache, no API is calling, with 0 cost and the 0 input tokens, output tokens count in this case. Okay? If we go to check the prompt caching that already used by the Claude, and see also, there also had a lot of steps, and they will show only the final result to save time. This is without prompt caching result, output result, and this is with prompt caching result. If we go firstly with without prompt caching, we can see for every call of the user, okay? Every questions he count input and the output tokens and also calculate the total cost. And for the next questions, same issue. He make the calculate count the input tokens and the output tokens and also the total cost. Okay? Now I hear in call number 5, the user asking the same questions as the first one in call number 1. However, the input tokens, the output tokens is counting, still counting, and they pay for it. Okay? This for without prompt caching. After enable prompt caching in this way, we can see the same user, okay, ask the first questions. In this first question is counting and cache creation input tokens. Okay, this had a cost. And the cache read input tokens in this case is 0. Once the user in second call make a questions, can I return the same item? In this case, the first tokens that will count in the creation input token now convert to count and read input tokens because this is already second time. Okay? With also the cost for cache read input tokens and for normal fresh input tokens that is different, okay? Between save the first call and the output tokens, and it calculates the cost. In call number 5, the user asks the same questions as the first call. What is your standard shipment type? In this, you see their count in cache read input tokens, and they have a cost. If you compare call number 5 with call number 1, okay, the only saving here is this. First, here is the cost for cache creation input token, and the call number 5 is reflected, or counting in cache read input tokens, that they have less cost, okay, regarding to the cache creation input tokens. And this the idea. The idea is prompt caching is every user questions, make API call, and the all tokens are counting. But for the cache read input tokens is counting or cost take a very low cost compared to normal input tokens or creation, cache creation input tokens. So here, for the same call, the total cost is $0.00886. And for the fifth, the call number 5 that calls the same questions, we have total cost of 0.0116. This is lowest than the first call. This is the idea of prompt caching. And here's the part I want you to walk away with. These two techniques are not competitors, they stack. Exact response caching catches the requests that are identical and removes them from the bill completely. Prompt caching catches everything else, the requests that do need a fresh model call, and reduces the cost of the shared context inside them. Run both, and you're paying full price only for the genuinely new, genuinely unique part of your traffic. Everything else, exact repeats, and repeated context inside non identical requests, gets discounted or eliminated. So that's layer 3, technique 1. But exact caching has that hard limit we talked about. One typo, and it's a miss. Next episode, we fix that. Semantic caching asks not, is this the exact same text, but does this mean the same thing as something we've already answered? That opens caching up to all the rephrasing and typos that exact matching can't touch. See you in the next one.